In statistical test theory, the notion of statistical error is an integral part of hypothesis testing. Hypothesis testing or significance testing is a method for testing a claim or hypothesis about a parameter in a population using data measured in a sample. Hypothesis testing is the art of testing if variation between two sample distributions can be explained through random chance or not. In any hypothesis testing problem, there are two contradictory hypotheses under consideration. If the hypothesis regarding the population parameter were true, the test requires an unambiguous statement of a null hypothesis, which usually corresponds to a default state of nature. For example, this person is healthy, this accused is not guilty, or this product is not broken. An alternative hypothesis is the negation of null hypothesis. For example, this person is not healthy, this accused is guilty, or this product is broken. The result of the test may be negative relative to null hypothesis, that is, not healthy, guilty, broken, or positive, that is, healthy, not guilty, not broken. If the result of the test corresponds with reality, then a correct decision has been made. However, if the result of the test does not correspond with reality, then an error has occurred. Due to the statistical nature of a test, the result is never, except in very rare cases, free of error. Two types of error are distinguished: type 1 error and type 2 error. Type 1 and type 2 errors are probability of committing mistakes in testing a hypothesis. A type 1 error occurs when the results of research show that a difference exists, but in truth there is no difference. So the null hypothesis, that is H0, is wrongly rejected when it is true. If we have to conclude that two distributions vary in a meaningful way, we must take enough precaution to see that the differences are not just through random chance. At the heart of type 1 error is that we don't want to make an unwarranted hypothesis, so we exercise a lot of care by minimizing the chance of its occurrence. Traditionally, we try to set type 1 error as 0.05 or 0.01, as in there is only 5% or 1% chance that the variation that we are seeing is due to chance. This is called the level of significance. Again, there is no guarantee that 5% is rare enough, so significance levels need to be chosen carefully. The statistical power is the ability of a test to detect an effect if the effect actually exists. A statistical power analysis is either retrospective, that is post hoc, or prospective, that is a priori. A prospective analysis is often used to determine a required sample size to achieve target statistical power, while A retrospective analysis computes the statistical power of a test given sample size and effect size. In this module, our focus will be on type 2 error of hypothesis and the power of test.
After studying this module, we shall be able to understand the concept of type 2 error, learn to calculate the type 2 error, and lastly, we shall be able to learn the concept of statistical power test. The notion of statistical error is an integral part of hypothesis testing. The test requires an unambiguous statement of a null hypothesis, which usually corresponds to a default state of nature. For example, this person is healthy. An alternative hypothesis is the negation of null hypothesis. For example, this person is not healthy. The result of the test may be negative, relative to null hypothesis, that is not healthy, or positive, healthy. If the result of the test corresponds with reality, then a correct decision has been made. However, if the result of the test does not correspond with reality, then an error has occurred.
Another important approach of hypothesis testing is p-value instead of a critical value. P-value is a probability of obtaining a sample mean given that the value stated in the null hypothesis is true. It varies between 0 and 1 and can never be negative. The p-value for obtaining a sample outcome is compared to the level of significance. Level of significance describes a decision made concerning a value stated in the null hypothesis. If the calculated p-value is smaller than the probability in the rejection region, then the null hypothesis is rejected. If the calculated p-value is greater than or equal to the probability in the rejection region, then the hypothesis will not be rejected. When the null hypothesis is retained, we fail to reach significance. The p-value approach is popular today because p-values are usually computed by statistical software packages including Excel and Minitab. The advantage to reporting test results using a p-value is that it provides more information than simply stating whether the null hypothesis is rejected. The decision maker is presented with a measure of the degree of significance of the result, that is the p-value. This allows the reader the opportunity to evaluate the extent to which the data disagrees with the null hypothesis, not just whether they disagree. However, there are a few important points which one should always keep in mind. P-value is a probability assuming null hypothesis is true. It is not the probability that null hypothesis is true. To determine the p-value, we must first decide which value of the test statistics are at least as contradictory to null hypothesis as the value obtained from our sample.
In statistical testing, when the result of the test does not correspond with reality, then that indicates that an error has occurred. This can be of two types, type 1 error and type 2 errors. These errors are probability of committing mistakes in testing a hypothesis. Type 1 error occurs when results of research shows difference exists, but in truth there is no difference. That is, H naught is wrongly rejected when it is true. On the other hand, type 2 error occurs when null hypothesis is accepted, but the alternative is true. That is, H naught is not rejected when it is false. Let us take an example to understand type 2 error. In a clinical trial of a new drug, the null hypothesis might be that the new drug is no better on average than the current drug, that is, H naught. There is no difference between the two drugs on average. A type 2 error would occur if it was concluded that the two drugs produced the same effect, that is, there is no difference between the two drugs on average, when in fact they produced different ones, that is, you have accepted H naught when it was false. The probability of a type 2 error is generally unknown and is symbolized by beta and described as P type 2 error is equal to beta.
Decide to retain the null hypothesis, we can be correct or incorrect. The correct decision is to retain a true null hypothesis. This decision is called a null result or null finding. This is usually an uninteresting decision because the decision is to retain what we already assumed, that the value stated in the null hypothesis is correct. For this reason, null results alone are rarely published in behavioral research. The correct decision is to retain a false null hypothesis. This decision is an example of a type 2 error or B error. With each test we make, there is always some probability that the decision could be a type 2 error. In this decision, we decide to retain previous notions of truth that are in fact false. While it is an error, we still did nothing. We retained the null hypothesis. We can always go back and conduct more studies. When we decide to reject the null hypothesis, we can be correct or incorrect. The incorrect decision is to reject a true null hypothesis. This decision is an example of a type 1 error. With each test we make, there is always some probability that our decision is a type 1 error. A researcher who makes this error decides to reject previous notions of truth that are in fact true. Making this type of error is analogous to finding an innocent person guilty. To minimize this error, we assume a defendant is innocent when beginning a trial. Similarly, to minimize making a type 1 error, we assume the null hypothesis is true when beginning a hypothesis test. Type 1 error is the probability of rejecting a null hypothesis that is actually true. Researchers directly control for the probability of committing this type of error. An alpha A level is the level of significance or criteria for a hypothesis test. It is the largest probability of committing a type 1 error that we will allow and still decide to reject the null hypothesis. Since we assume the null hypothesis is true, we control for type 1 error by stating a level of significance. The level we set, called the alpha level, symbolized as A, is the largest probability of committing a type 1 error that we will allow and still decide to reject the null hypothesis. This criteria is usually set at 0.05, that is A is equal to 0.05, and we compare the alpha level to the p-value. When the probability of a type 1 error is less than 5%, that is p is less than 0.05, we decide to reject the null hypothesis. Otherwise, we retain the null hypothesis. The correct decision is to reject a false null hypothesis. There is always some probability that we decide that the null hypothesis is false when it is indeed false. This decision is called the power of decision making process. It is called power because it is the decision we aim for. Remember that we are only testing the null hypothesis because we think it is wrong. Deciding to reject a false null hypothesis then is the power in as much as we learn the most about populations when we accurately reject false notions of truth. This decision is the most published result in behavioral research.
We can illustrate the type 2 error through a diagram. In this diagram, the blue curve represents sampling distribution of null hypothesis, that is, mu is equal to 0. The green curve represents sampling distribution of alternate hypothesis, that is, mu is equal to 1. The vertical red line shows cutoff region for null hypothesis, that is, the null hypothesis is rejected for values of the test statistic to the right of the red line and not rejected for values to the left of the red line. The probability of type 1 error is shown by the area to the right of the red line and below the blue curve alpha. And the probability of type 2 error beta is the area of the horizontally hatched region to the left of the red line and under the green curve beta. Let us learn how to mathematically calculate type 2 error with the help of an example. Suppose the mean weight of king penguins found in an Antarctic colony last year was 5.2 kg. Assume the actual bean population weight is 5.4 kg and the population standard deviation is 0.6 kg. At 0.05 significance level, we have to find out the probability of having type 2 error for a sample size of 9 penguins. Firstly, we will get the value of normal variate Z at 0.05 level of significance with the help of Z table. It comes out minus 1.645. Now we will compute the critical value C by substituting the values of H0, HA, sigma, N, and the critical value of Z at 0.05 significance level. We get, hence, value of C is 4.87. Now, having found the critical value, that is the value of C, let's find out the value of beta with the help of formula where sigma represents standard deviation, small n is sample size, and x bar is mean. In the formula, take beta to the left-hand side and the other values to the right-hand side. Substitute the values in the above equation. Now we see the probability at Z is greater than minus 2.65 in the Z table. It is equal to 0.9960. After substituting this value, we get the value of beta equal to 0.0040. Hence, the probability of type 2 error rate value is 0.0040.
The power in hypothesis testing is the probability of rejecting a false null hypothesis. Especially, it is the probability that a randomly selected sample will show that the null hypothesis is false when the null hypothesis is indeed false.
Let us now understand power of test. The probability of not committing a type 2 error is called the power of a hypothesis test. Hence, power is the probability of correctly rejecting a false null hypothesis. Power of a test measures the ability of a test to detect an alternative hypothesis. It is the probability that the test will correctly lead to the rejection of a false null hypothesis. That is, the probability that the test will reject H0 when that specific alternative is true. The statistical power is the ability of a test to detect an effect if the effect actually exists. Power of a test is equal to 1 minus beta.
The power of the test, which is 1 minus beta, that is the complement of beta, indicates the sensitivity of the statistical test in detecting changes that have occurred by measuring the probability of rejecting the null hypothesis when in fact it is false and should be rejected. The power of statistical test depends on how different the actual population mean really is from the value being hypothesized under H0. The value of beta used and the sample size. If there is a large difference between the actual population mean and the hypothesized mean, the power of the test will be much greater than if the difference between the actual population mean and the hypothesized mean is small. Selecting a larger value of beta makes it easier to reject H0 and therefore increases the power of a test. Increasing the sample size increases the precision in the estimates and therefore increases the ability to detect differences in the parameters and increases the power of a test.
Let us discuss the factors that affects the power of a test. Sample size n. Other things being equal, the greater the sample size, the greater the power of the test. Significance level alpha. The higher the significance level, the higher the power of the test. If you increase the significance level, you reduce the region of acceptance. As a result, you are more likely to reject the null hypothesis. This means you are less likely to make a type 2 error. Hence, the power of the test is increased. Effect size. To compute the power of the test, one offers an alternative view about the true value of the population parameter, assuming that the null hypothesis is false. The effect size is the difference between the true value and the value specified in the null hypothesis. Understand effect size with the help of an example. Suppose the null hypothesis is that a population mean is equal to 100. A researcher might ask, what is the probability of rejecting the null hypothesis if the true population mean is equal to 90? In this example, the effect size would be 90 minus 100, which equals minus 10. Hence, the greater the difference between the true value of a parameter and the value specified in the null hypothesis, the greater the power of the test. That is, the greater the effect size, the greater the power of the test. To these three factors, the value of power of test is also affected by the use of one-tailed rather than two-tailed. It has been observed that the power of one-tailed test increases sharply and approaches 100% for situations in which the actual mean really exceeds the hypothesized mean. The converse would be true. The larger the actual mean compared with the hypothesized mean, the greater is the power. On the other hand, for two-tailed tests, the greater the distance between the actual mean and the hypothesized mean, the greater the power of the test. Using the calculated value of beta from the above example, we calculate the power of the test, that is, 1 minus beta, that is, 1 minus 0.0040 is equal to 0.996. The magnitude of power has a strong effect in this illustration. Based on the value of the power, we can conclude about the magnitude of the test. If value lies between 0.00 to 0.15 or 0.85 to 1.00, it has a strong effect. If value lies between 0.15 to 0.35 or 0.65 to 0.85, it has a moderate effect. If value lies between 0.35 to 0.49 or 0.51 to 0.65, it has a weak effect. In this module, we have learned about type 2 error, that is defined as the probability of failing to reject a false null hypothesis. It is denoted by beta. The probability of not committing a type 2 error is called the power of a hypothesis test. We have also studied how to calculate both type 2 error and the power of test. Lastly, we have discussed the effect of different factors on power of test. If we increase power, we reduce beta. We reduce the probability of getting a type 2 error. A one-tailed test is more powerful than a two-tailed test and should be used whenever it is appropriate to specify the direction of the alternative hypothesis. An increase in the size of the sample n chosen results in an increase in power. A decrease in the size of the sample selected results in a decrease in power.